Bonds are like springs. If you've taken a physics class, you might have modeled the frequency of a spring using Hooke's law. And indeed, you can do that in IR as well, where you have our wave number over here, or it's basically like a frequency, is equal to a constant, and then that's the square root of the force. In other words, the strength of the bond. And so the stronger the bond is, the higher the frequency is, the higher the wave number is. Whereas mass is on the bottom of this equation, and so smaller masses lead to higher frequency. So that translates that into where we see different functional groups in an IR. And so CH, OH, NH bonds are going to be on the left. We've got that small proton there. And then strong bonds are also going to be towards on the left side of that 1500 delineation between the functional group region and the fingerprint region. The fingerprint region is filled with just single bonds that aren't CH bonds. So our carbon-carbon bonds are in that region, as well as these other ones, and they just end up being so many that it's really hard to interpret. There's tables. These are correlation tables, and what they do, or this is an example of a correlation table for IR, where it gives you the wave number and then the functional group that you would find at that wave number. And so going back to the same IR that we saw in the previous recording, we have this band around 3,500, one around 1,700, and then this 3,000 band. And so looking at what this probably is, it's an OH, and then that CH group for that 3,000. And then we also have the carbonyl around 1,700. So let's look at a couple like a few more subtle pieces about the IR. One is what happens when you have resonance in your functional group. So if we look at or compare the spectra of the ester and the amide that are shown here, the amide, the resonance structure where there's a carbon-nitrogen double bond is more important than the one on the left. It's more significant, and so, or than the structure on the left. And so the carbon-oxygen bond actually has a lot of single bond character. And so because it has single bond character, that shifts the carbonyl to a lower number than we usually see. Whereas for an ester, it is more significant to have a carbon-oxygen double bond. That's a more significant resonance structure, and that shifts that carbonyl to the left, to the more double bond side of the IR. Another thing to note is this band over here at about 3,500. That's really indicative of an OH group or something that's hydrogen bonding, and its position suggests that it's an OH group. And the wider bond comes from there being a range of connections, or a range of lengths and strengths of hydrogen bonds in a sample. And so when you have a longer or weaker hydrogen bond, that corresponds to a shorter, stronger covalent bond, and then vice versa here. Basically what's happening is this hydrogen-oxygen bond is taking electron density away from the oxygen-hydrogen bond over here on the left, the covalent bond. And when it's smaller, it takes more away. And so that weakens this OH bond. So in any case, you get a range of bond lengths and bond strengths for OH, and that's why you get this broad band. If you get a really dilute sample of alcohol, you see that the hydrogen bonding goes away, and you end up with a much sharper band over here to the left. Another thing to note is that there's a variety of intensities of bands. In other words, they're transmittances. And so on the left hand here, we have this very intense OH. There's probably only one OH group in this molecule, whereas, and this carbonyl is also very intense. That's because when you have stretches, there's a big change of dipole, and that really grabs on to that IR light. And so you end up seeing a high transmittance, or pardon me, a low transmittance, a high absorbance. This bond right here, or this band right here, is the CH, and there's probably just a whole bunch of CHs. As it vibrates, its dipole doesn't change very much at all, but there's a whole bunch of CHs, so you end up having a low transmittance as well, high absorbance. We can see some of these bands to the right are much smaller by comparison. And so just recognize that that difference of intensity does tell you something about the functional group. If you know that you only have one of those groups in there and it's a really big band, then, or a really intense band, then you know that there has to be a change of dipole. And on the other side of that, it is possible to have molecules that are missing bands, and that could be because it's a symmetric stretch. And so that is an inactive IR vibration. Now you still will have other vibrations that are visible, and so it will just be missing one. Carbon dioxide does that too. And then a final note about the fingerprint region. Here we have two different molecules. One's a ketone, one's an ester. And you can see that the functional group region is really very similar. We couldn't use that functional group region to distinguish between these two molecules. But you can see on the right side, the fingerprint region, they're really different. And so that can tell you that you have different molecules. And again, if you can find, if you're kind of sure what you made or that you have, then you can compare it to a standard IR.